To calculate the maximum amperage that the utility must supply during soft starting of an asynchronous motor, several factors need consideration. Firstly, the motor's full load current, which is 520 amps. Secondly, the soft start current limit with a maximum of 600 amps. Thirdly, the soft start current factor, which typically ranges from 1.2 to 2.0 for asynchronous motors. In ramp start mode, the maximum starting current can be calculated by multiplying the current factor K by the motor's full load current IFL. Assuming a K value of 2.0, the maximum starting current would be 2.0 times 520 amps, resulting in 1040 amps. In kickstart mode, the maximum starting current is limited by the soft start current limit, which in this case is 600 amps. Therefore, the utility should be capable of supplying a maximum of 1040 amps for ramp start mode or 600 amps for kickstart mode to prevent any starting current related issues. Utilizing the current limit option in the soft starter offers a solution to constrain the starting current to the maximum capacity of the utility, which is between 500 to 600 amps. By configuring the current limit to, say, 500 amps, the soft starter will gradually increase the motor current during startup, ensuring it stays within the utility's limit. This strategy guarantees a smooth startup without causing any problems. Now let's shift the focus to ignition wire selection for a flare or burn pit system. When selecting ignition wires, several factors are crucial. Firstly, distance is not typically a significant concern, particularly for shorter distances. However, over longer distances, the wire's resistance can become a factor, potentially affecting ignition performance. Secondly, the burial of ignition cables is essential to protect them from physical damage, moisture, and environmental elements. Generally, a burial depth of around 12 to 18 inches is considered standard. Other factors to consider when selecting ignition wires include the voltage rating, insulation, resistance, and flexibility. Ignition wires must have a voltage rating that aligns with the ignition system's voltage requirements. High temperature insulation is necessary to withstand the harsh conditions present in a flare or burn pit system. Low resistance ignition wires are preferable as they minimize voltage drop and enhance ignition performance. Ignition wires should possess adequate flexibility to facilitate easy installation and handling. Let's explore these factors in more detail. Starting with the motor, it's an asynchronous motor, also known as an induction motor. These motors are widely used due to their robust construction, reliability, and relatively low cost. However, they do present a challenge during startup, as they draw a high inrush current, which can be several times the full load current. This inrush current can cause voltage dips in the power supply, potentially affecting other equipment connected to the same grid. To mitigate this issue, soft starters are employed. A soft starter is an electronic device that gradually increases the voltage applied to the motor during startup, thereby reducing the inrush current. It typically uses thyristors, also known as silicon-controlled rectifiers or SCR, to control the voltage. The soft starter can be configured to operate in different modes such as ramp start and kickstart. In ramp start mode, the voltage is gradually increased from a low level to the full voltage over a period of time. This provides a smooth and controlled start, minimizing the inrush current. The duration of the ramp can be adjusted to suit the specific application. In kickstart mode, a small initial voltage is applied to the motor to get it rotating, and then the voltage is quickly ramped up to the full voltage. This mode is useful for applications where a quick start is required. The soft start current factor, denoted as K, represents the ratio of the maximum starting current to the full load current. This factor depends on the motor design and the load characteristics. A typical value for K is between 1.2 and 2.0 for asynchronous motors. The current limit option in the soft starter allows you to set a maximum current that the motor can draw during startup. This is particularly useful when the utility has a limited capacity. By setting the current limit to a value below the utility's capacity, you can ensure that the starting current does not cause any problems. When selecting ignition wires for a flare or burn pit system, it's crucial to consider the environmental conditions. These systems often operate in harsh environments with high temperatures, exposure to chemicals, and potential for physical damage. Therefore, the ignition wires must be robust and able to withstand these conditions. The voltage rating of the ignition wires should be sufficient to handle the voltage used in the ignition system. Typically, ignition systems operate at relatively high voltages to generate a spark that can ignite the fuel. The insulation of the ignition wires must be able to withstand high temperatures and resist chemical attack. Common insulation materials include silicone rubber, fiberglass, and Teflon. The resistance of the ignition wires should be low to minimize voltage drop and ensure a strong spark. Copper is a common conductor material due to its low resistance. The flexibility of the ignition wires is important for ease of installation and maintenance. The wires should be able to bend and flex without cracking or breaking. In addition to these factors, the burial depth of the ignition cables is also important. Burying the cables protects them from physical damage, moisture, and UV radiation. The recommended burial depth is typically 12 to 18 inches, but this may vary depending on local codes and regulations. The National Electrical Code, or NEC, provides guidelines for the installation of electrical cables, including ignition cables. It is important to consult the NEC and local codes to ensure that the installation meets all requirements. For instance, NEC Article 300.5 details underground installations. Some additional considerations for ignition wire selection include the following: 1. Shielding. Shielded ignition wires can help to reduce electromagnetic interference, or ME, which can disrupt the operation of other electronic equipment. 2. Strain relief. Strain relief should be provided at the points where the ignition wires connect to the ignition system and the flare or burn pit. This will prevent the wires from being pulled or strained, which could damage them. 3. Labeling. The ignition wires should be clearly labeled to identify their purpose and voltage rating. This will help to prevent accidental misconnections. 4. Testing. The ignition wires should be tested after installation to ensure that they are properly connected and functioning correctly. This can be done using a multimeter or other testing equipment. 5. Maintenance. The ignition wires should be regularly inspected for damage and wear. Damaged or worn wires should be replaced immediately. When dealing with motor starting, it's also important to understand the concept of motor overload protection. Overload protection is designed to protect the motor from overheating due to excessive current draw. This can be caused by a variety of factors, such as a stalled rotor, a heavy load, or a short circuit. Overload protection devices, such as thermal overload relays or electronic motor protection relays, are used to monitor the motor current and trip the circuit breaker if the current exceeds a predetermined value. The overload protection device should be sized appropriately for the motor's full load current and service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. A motor with a service factor of 1.15 can handle a 15% overload for a short period of time without overheating. It's also important to consider the motor's starting method when selecting overload protection. Motors that are started using a soft starter typically have a lower starting current than motors that are started across the line. Therefore, the overload protection device can be set to a lower value for soft-started motors. In addition to overload protection, it's also important to provide short-circuit protection for the motor. Short-circuit protection is designed to protect the motor and the electrical system from damage in the event of a short circuit. Short-circuit protection devices, such as fuses or circuit breakers, are used to quickly interrupt the current flow in the event of a short circuit. The short-circuit protection device should be sized appropriately for the motor's locked rotor current, which is the current that the motor draws when it is initially started. The locked rotor current is typically much higher than the motor's full load current. When selecting a soft starter, it's important to consider the motor's horsepower, voltage, and full load current. The soft starter should be sized appropriately for the motor's characteristics. It's also important to consider the application requirements, such as the starting frequency, the load characteristics, and the ambient temperature. Soft starters are available in a variety of sizes and configurations to meet different application requirements. Some soft starters include advanced features such as current limiting, voltage ramping, and motor protection. These features can help to improve the motor's performance and protect it from damage. When installing a soft starter, it's important to follow the manufacturer's instructions carefully. The soft starter should be properly grounded and connected to the motor and the power supply. The soft starter should also be programmed correctly to ensure that it operates properly. Regular maintenance is essential to ensure the continued reliable operation of the motor and the soft starter. The motor should be inspected regularly for signs of wear and damage. The soft starter should also be inspected regularly for loose connections, damaged components, and proper operation. Any problem should be corrected promptly to prevent further damage. Now let's delve a bit more into the specifics of ignition wire insulation. Different types of insulation offer varying degrees of protection against heat, chemicals, and abrasion. Silicone rubber is a popular choice due to its excellent heat resistance and flexibility. It can withstand temperatures up to 200 degrees Celsius or 392 degrees Fahrenheit, making it suitable for many flare and burn pit applications. Fiberglass insulation is another option that offers good heat resistance and is relatively inexpensive. However, it is not as flexible as silicone rubber and can be more susceptible to abrasion. Teflon insulation, also known as polytetrafluoroethylene or PTFE, provides excellent resistance to heat, chemicals, and abrasion. It can withstand temperatures up to 260 degrees Celsius or 500 degrees Fahrenheit, making it suitable for demanding applications. However, Teflon insulation is more expensive than silicone rubber or fiberglass. The choice of insulation material will depend on the specific requirements of the application and the budget. It's also important to consider the thickness of the insulation. Thicker insulation provides better protection against heat, chemicals, and abrasion, but it also makes the wire less flexible. The appropriate insulation thickness will depend on the voltage rating of the wire and the environmental conditions. In addition to the insulation material and thickness, the construction of the ignition wire also plays a role in its performance. Ignition wires typically consist of a central conductor surrounded by insulation. The conductor can be solid or stranded. Stranded conductors are more flexible than solid conductors, but they may also have a slightly higher resistance. The number of strands in the conductor also affects its flexibility. More strands result in a more flexible wire. The insulation can be applied in a single layer or multiple layers. Multiple layers of insulation provide better protection against heat, chemicals, and abrasion. The ignition wire may also include a shield to reduce electromagnetic interference, (ME). The shield is typically made of braided copper or aluminum and is grounded to provide a path for unwanted electrical noise. Shielded ignition wires are often used in applications where EMI is a concern, such as near sensitive electronic equipment. When selecting ignition wires, it's important to consider all of these factors to ensure that the wires are suitable for the specific application. It's also important to consult with a qualified electrical engineer or technician to ensure that the installation meets all applicable codes and regulations. Remember to always prioritize safety when working with electrical equipment and systems. Follow all safety precautions and use appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working with electrical equipment, it's best to hire a qualified electrician to do the work. By carefully selecting and installing ignition wires, you can ensure the safe and reliable operation of your flare or burn pit system.